fare il pigeon. Oh.
Meneer de kandidaat, u bevindt zich tegenover een commissie, aangewezen door het College voor Promoties, die bereid is met u van gedachten te wisselen over het proefschrift en de erbij gevoegde stellingen. De gedachtenwisseling wordt aangevangen door Dr. Vonk en ik heet hem graag welkom.
Veel dank. Meneer de kandidaat, I would like to begin by saying thanks for a nice thesis, which I greatly enjoyed reading. And whilst reading, I had a few questions. I'd like to begin with a comment that you make on page 62, where you say the following. So this is in chapter 2 about the uniform bounds for elliptic curves over Q. You say, we prove our estimates by group theoretic means. The advantage of such an approach is that our methods can easily be extended to number fields other than Q. You mentioned this again in remark 3.15, where you contrast it with the method of Rouse, Sutherland, and Sereg-Brown. And I was wondering if you would be willing to reflect on a comparison between the two methods and why you believe that your methods should be more easily amenable to generalization.
Thank you for your question, Sir geëerde opponents. Yeah, so I can first comment on my methods, maybe. Our methods mainly rely on finding specific elements inside the Galois group or inside its image under the Galois representation. Specifically, we need homotheties, so elements that are in the center of this group. And yeah, so this is less, I would say, less precise than the method used by Rouse and his collaborators, in that it doesn't give a full description of the image. It just we just say we need to find certain elements, and we don't really care about the full picture of the image. So the main difference is possibly that they try to be extremely precise in describing the full group, and we just need to find some certain properties. Yeah, but it is in general, because of this, probably it's easier to generalize, because we don't find such a detailed description, but we just use certain techniques to find certain elements, which is, for example, possible to do at least for curves over totally real fields. I believe it's somehow possible to generalize these methods at least. But yeah, I guess the answer is that our methods are less precise. We just find enough elements inside the image rather than finding a full description. So this is why they're easier to extend.
And would there be significant difficulties in extending the approach of the other team of people?
Well, I believe so, especially if you I'm not so sure how much of a difficulty would come from extending over different base fields than how much it would come from extending to primes other than 2 or 3. They solved the problem for the prime 2. For the prime 3, I think it's still work in progress. And their method relies on finding a modular curve that describes all the possible images. And for the prime 2, it was somehow manageable. For 3 is harder, but maybe they can still do it. For higher primes, it's even harder. And I think if you move over, I'm not very familiar with modular curves, but I guess if you move over higher degree fields, then it also becomes more difficult to study them. So.
Certainly, yes, I agree with that. So maybe while we're in the neighborhood, I might as well ask you also, you mentioned uniformities in the title of this chapter.
Yep.
Of course, you mean uniformity in the elliptic curve. But if we're talking about number fields, there is a different way to interpret the word uniformity. For instance, we could ask if there's uniformity in the number field when we fix the degree of that number field over Q. Do you have any prospects there in generalizing your methods to get also such uniformity results?
Okay, let me think. I don't think we have, at the moment, a uniform result over general number fields. So even if we fix one field which is not Q, I think it might be possible for some fields. And then if we do this, maybe extending to uniformity over a family of fields of bounded degrees could be possible. But I'm not
for instance,
sure.
quadratic fields. But there's, for instance, work of Mirel, which establishes such uniformity bounds, and perhaps you can rely on that in similar ways that you rely on the work of Barry Meza in your theorems.
Yes. Yes, in the end, it depends on the possible images of Galois representations, well, on the, not just the modulo P, but also the p-adic representations. So if those are somehow uniformly, let's say there's only a finite amount of possible images for fields of degree 2, then yes, of course, we can have uniform results. But yeah, how close we are to getting it, I think it's not very close.
Sure, yeah, no, it's probably still quite a difficult question. I don't know if I have time maybe for another question.
Sure.
I was wondering, in your argument, the main theorem that you prove in this chapter, which is theorem 3.4, you rely on the explicit knowledge of the full set of rational points on certain modular curves. So you rely, for instance, when you talk about the 13-adic image, you rely on a result of the full knowledge of rational points on the non-split Cartan modular curve.
Yes.
And then you avoid having to use that result for the S4 case, the exceptional image, which appears also in your proof. You avoid doing that with a group theoretic trick, and you remark after the proof that a simplification of the proof is possible if we instead invoke also a more recent result on the full set of rational points on this modular curve with S4 level structure.
Can you remind me what page we saw?
So this is, I probably can. So this is in chapter 2, theorem 3.4, I think, if I recall correctly.
I have a proposition 3.4.
Sorry, no, chapter 3.4, so it's theorem 3.16.
Okay.
Yes. And so in remark 3.17, you talk about this simplification relying on the knowledge of the set of rational points on a modular curve. Now, are similar simplifications possible if you knew the set of rational points on any modular curve that you like? And if so, what would be the interesting modular curves to know the rational points on?
Well, as I said, I'm not very familiar with modular curves, so we mainly rely on this result as already done by some other people, and we take the result. I'm not very familiar with the method used to get these results. So there's a modular curve mentioned here.
So for instance, in the 3-adic image, there is also modular curves that you could consider of level 27, where the set of rational points is not known, but perhaps it could lead to similar simplifications in the proof.
Oh. I'm sorry, I'm afraid I don't know how to answer this.
Maybe this speaks to the power of your methods, because I think these rational points are possibly findable in the future, but they have not as of yet been done. But somehow in your proof, you don't need to know them.
Yeah, we don't need to know
your methods.
much. Yeah, exactly. Yes. Of course, if we knew, so many things that we did in this chapter could be simplified if some conjectures that are at this point a conjecture actually become proved. For example, full description of the possible images, or the fact that for primes higher than 37, the modulo P representation is always surjective. This is at this point still a conjecture, and we use what is known to find certain elements.
Precisely.
But this makes the proof more difficult in some cases. But if in the future these conjectures are proved, then we can simplify greatly these methods, yes.
Fantastic. But I think it speaks to the power of your methods that you do not need to rely on such kind of hypothetical theorems. So I think with that, I have asked most of my questions, so perhaps I give the word to the next opponent.
Thank you. The examination shall be continued by Dr. Salgado from the Rijksuniversiteit Groningen. We're very pleased that you participate in today's discussion, and the same applies to the other guests today, Professor Thalman from the University of Amsterdam and Professor Wiese from the Université de Luxembourg. But now, Dr. Salgado, the floor is yours.
Thank you very much. Meneer kandidaat. So I will start by saying that I really like it to read. So I really learned a very good deal of nice mathematics. And I would like to start from the beginning. So let's go to page 16, to your main theorem, theorem 1.1. And my question is that you are dealing during your thesis mostly with elliptic curves over Q and sometimes over number fields. My question is if you could say a little bit of what you think would happen if you replace them for a function field, for instance.
Thank you for your question, zeer geleerde opponents. As we can see at the end of my thesis, the main idea, well, very general idea, is that we can reduce all the properties of Kummer extensions to properties of torsion fields, right? So, and this can, I think the way I formulated it in the end of my thesis, this reduction to the torsion fields can be done also over function fields. If a characteristic is not zero, then we have to pay attention in some cases maybe. But yeah, so my answer would be if all the properties for the torsion representations over function fields still hold, or similar properties hold, then yes, we can extend the results. I have not studied the Galois representations of elliptic curves over function fields, so I don't know to what extent results such as Serre's open image theorem hold, or similar results may hold. But if we have analogs, then yes, we can extend the work.
Okay, thank you very much, meneer kandidaat. I will then move to page 39 and 40, where you have your theorem 4.17. And you have two bounds there. You produce one bound in the CM case and one in the non-CM case.
Yes.
And then on the CM case, so on the non-CM, right, you have a bound which is not as sharp as a bound of, I think, Serkia, right, and maybe Rouse also. But then you have a second bound for the CM case. And I'm wondering how sharp this bound is.
In many of these cases, we do not prove that the bounds are sharp, and I think they are not. What we know is that all the primes that appear, well, in this general form, maybe not, but in the second chapter where we actually have an explicit constant, we know that all the primes that appear there must appear. So they are not sharp as for exponents, but they are sharp as in the other direction, let's say. Yeah, so for the CM case, we do not have many examples over number fields higher than Q, so I find it easier to reply to these questions using the results of chapter 2, if you agree. So over Q, we have, I don't know, we had some examples of curves that show a failure with certain primes that divide the failure of maximality. Let me see. There are some tables here. Okay, on page 96 and 97. There are some tables with some curves that show for each of the primes that appear in our uniform constants over Q, a curve that shows failure of maximality, which is a multiple of that prime. So in general, I would say probably the same kind of results holds, that the primes that we mentioned, we expect them to appear for some curve over some field, but maybe not the V exponent that we found, maybe with a lower exponent.
Thank you. We have time for one more question.
A short one.
Okay, so let's stay close to what you're talking now, at least close to chapter 2. So you have a theorem 4.8 on page 85, where you give here, so you say that the exponent has to divide this large
Yes.
product of prime numbers. But then later, around the page that we're talking about now, around 95 and 94, you have these examples, right, where the exponents are always the power of a prime. So do you know examples where you have maybe a product of two primes, of two different primes, or what do you think is going to happen?
So with two primes, probably it is possible with the prime 2 and a higher prime. In general, we had this conjecture and we wanted to work on it, but we didn't have time, my collaborator and I, that not too many of these primes can appear. So for example, 2 primes higher than 5 probably cannot both appear or something close. So yeah, so my idea is that all these primes together cannot appear for sure, but we did not prove this. So our conjecture is that only a few of the primes can appear.
Could you comment on why? You don't expect that 5 times 7, or?
The thing is, if we look at a simpler problem, over Q, we cannot have both a 5 torsion point and a 7 torsion point, right? So this is a simple problem. Of course, in more general cases, like we don't need a torsion point to have a factor in this product, but we need the non-surjectivity of the Galois representation. But I think we cannot have it for both 5 and 7 at the same time for the same curve.
Okay. Maybe then I think that I am very happy with my question so far. Thank you very much.
Thank you. The examinations will be continued by Professor Taalman of the University of Amsterdam.
Thank you, Mr. Candidate. Thanks for your thesis, which I much enjoyed reading. I was spending time on trains last week. There were still trains running last week. I would like to ask you to ask one of your paronyms to read aloud proposition 1 from the Stellingen attached to the thesis.
The failure of maximality of Kummer extensions of number fields arising from non-torsion points on elliptic curves is bounded by a constant that depends only on computable quantities associated with the base field, with the chosen curve, and with divisibility properties of the chosen points.
Thank you. I was a little bit confused with the precise mathematical meaning of the phrase depends only on computable quantities. Could you perhaps comment a little bit on how I am to interpret this proposition?
Yes, thank you for the question, or geëerde opponents. Yes, so computable, we mean that are in principle computable, so that there exists a theoretical algorithm that produces these results. Unfortunately, in many cases, this theoretical algorithm, although in theory it works, in practice it's too slow.
So I understand correctly that you're saying that also the dependence is computable. So there is an algorithm that on input a number field and a curve and points outputs a bound.
Yes, because all the quantities we have, basically the main quantities that are at play here are these parameters of maximal growth for the torsion representation. And given a curve, one can start computing the images of the Galois representation modulo a prime p, modulo p squared, modulo p cubed. And of course, if a prime is higher than 2 or the power is higher than 3, then this becomes very slow with general methods for computing Galois groups. But if you do this, at some point, you'll find that, let's say, after p to the n, between p to the n and p to the n plus 1, the growth is maximal. And at that point, we know that we can stop, because after that, the growth is always going to be maximal, with some exceptions for 2 at low powers. But yeah. Yeah, and in this case, just given the curve and the number field represented in some way inside our computer, we can apply this method and it will not end before the computer degrades into atoms, but yeah, in theory it works.
Okay, thank you. So let's stick a little longer with this theoretical meaning of computability. So if I interpret it in that way, what would you need to generalize this proposition from elliptic curves to more general group schemes?
Yeah, so in general, the problem is not even the computable part, is even the, well, yes, it is the computable part, of course. We need, well, first of all, we need to be able to represent these commutative groups inside a computer, so we need to have a description of a group.
Let's say it's the Jacobian of a curve.
Yeah, okay.
To you.
We need explicit results for so our methods rely on let me think. Yes, I think some of the things. Okay, so for elliptic curves, we have results that depend only on these parameters, on these computable parameters. For the general case, I still have a similar result, but it depends on things that are. So one of the main points for elliptic curves was reducing for these p-adic parameters to having an adelic bound, which we could do, but we used the specific fact that the matrices were 2 by 2, so really explicit things. And in the general case, we still have an explicit dependence on the image of the adelic representation, which is in principle not computable, because you cannot simply raise the exponent. You have to raise in two directions. You don't know when you can stop. In this case, we have dependence on this thing, which is not entirely explicit. Maybe one can work and make it more explicit. This is probably future work for someone. But yeah, so far we do not have explicit dependence on the parameters of maximal growth, which are the computable things.
Okay, thank you very much. If there is time, I'd like to move on to another question.
One short question.
Okay, so then my next question is on proposition 2. I will not embarrass your paranymph with the question to read it aloud. Yes, then please go ahead.
I didn't understand what we need to do.
Position 2.
Yes.
The elliptic curve E over Q defined by the equation y squared plus y equals x cubed minus 216x minus 1861 is such that this point P, the rational point P written.
Maybe I should interrupt.
I think
it doesn't make sense to read this equation. So
I think we can.
please sit down,
you.
and
Okay.
we can all see the equation.
Yes. The essence is clear, I think. Yep. So my question is, I think, exactly about the fact that it is hard to read the equation. I was reading your thesis on a train, and so I was absolutely unable to verify the truth of proposition 2. For all it's worth, this could be random numbers to me. Would it be possible to give either heuristic or rigorous, pure thought argument that such a configuration at least exists, that there exists an E and a P with these properties?
Thank you for your question. The exact reason why I put this as a proposition is, well, first of all, it is one of my first autonomous results that I got in the last 4 years. And second, that it was not completely clear a priori that this would exist. There was a condition in a result by Rouse and Jones that if a modulo 3 representation, for example, is not surjective, then we might lose factors for the degree of Kummer extensions, and this loss of factor may or may not come from the existence of in that case, comes from the existence of a torsion point, but they did not provide an example for this. So the way I did it was to run a script that I wrote through thousands of curves, and after thousands of curves, it finally found one. The conductor of this curve is 17,739, I think, which is quite high, and it is the curve of the smallest conductor that shows this phenomenon. So it is not clear a priori that this should happen, I think.
Okay, thank you.
The examination shall be continued by Professor Wiese from the Université de Luxembourg.
Meneer de kandidaat, I'd also like to congratulate you on the nice results that you obtained during your research work, and also for this nice picture on the front page. It shows trees, and that brings me to my first question. So we can open the thesis at page 22, where you have a subsection called arboreal Galois representations. And now my question is, I mean, arboreal for me, has something to do with trees. Where are the trees here? Can you explain this to us, please?
Thank you for your question, geleerde opponents. Well, if you, the tree is a tree in the mathematical sense, so it's a connected graph without loops. In this case, is a rooted n-ary tree. If we take a number and divide it by, extract the nth roots, we obtain n of them. And for each of these n roots, we can extract its n roots and obtain n more roots. So we have a tree in which each node is one of these numbers, these roots. And at each next step, we have n more roots. So this is where the tree comes from. And the arboreal representation, the name comes from that we are using the action of this Galois group, interpreting this action on this tree, so permuting and rotating the branches of this tree.
Okay, thank you very much for this enlightening answer. Then I'd like to go back to theorem 1.1, which we already had a question about. So my question is about the dependence that you write in the way that you say that your constant C depends on the L-adic torsion representations associated to E for all primes L. And now my question is, or I'm wondering, why you write it in that way? Why don't you just write it depends on the curve?
Thank you for your question. I think we simply wrote it to make it more explicit, add some more details. And it is nice to know what kind of properties of a curve our results depend on, I think. So we could have written, let's say, depends only on E. We could also have said depends on computable properties of E, and the result is the same, it's exactly the same power, let's say. But yeah, we just felt like adding a few more details in the statement. It doesn't hurt.
Okay, thank you for this answer. I'd like to continue with, in the same spirit, if you replace the curve E now by an isogenous curve, can you make a link if you know something about E, and then you have E prime, which is isogenous?
So, yes, for sure, because the Galois representations of a torsion are linked. The precise extent to which the Kummer representation is linked, we have not studied it yet. So I don't know. I cannot answer at this point, but it's probably in the future someone will be able to answer.
Yeah, you could imagine the image of your point alpha under the isogeny, yes, and then see how the dependence changes under the isogeny. The Galois representation doesn't. Okay, thank you for this answer. And I would like to go on with maybe a question on lower bounds. So you give upper bounds, you have your divisibility constants, which are sort of upper bounds. And yeah, a natural question is lower bounds. You already told us that they're not, probably your bounds are not sharp, but maybe can you comment on the existence of lower bounds that you could maybe also make explicit?
So for example, the existence of surjective Kummer representations. I think in many cases we can expect to find surjective Kummer representation, so for the purely Kummer side, because for the torsion part, depends on the base field. For example, over Q, there are no curves with surjective adelic representation. There is an index of at least 2.
Indeed, yes.
But from the Kummer side, I think we can expect surjective representations in many cases, because the fact that the adelic representation is not surjective does not say that in essence, my results depend not really on the group theoretic image of the Galois representation, but on the ring generated, on the subring of the endomorphism ring of the torsion point generated by this image. So even incomplete images, let's say, can generate a more complete subring. And in that case, a non-surjective torsion representation still gives us all we need for a surjectivity on the Kummer side. So we did not elaborate too much on lower bounds, but also would be interesting to find examples of curves with surjective Kummer representation, but I believe that there are plenty.
Can I ask another question?
Sure.
Do you have some constructive approach or some ideas how you could construct curves with surjective alectic representation, for instance, or surjective Kummer representation? Or in other words, can you construct curves that have a certain C, for which you have exactly the failure of maximality?
So to find...
yeah, I give you 5 and you tell me number 5 there. Mm-hmm. Can you make a curve with failure of maximality 5?
Yes, well, we did. In chapter 2, we have examples.
Yeah,
the idea is that we have to
start...
Then
I changed 5 by some other number, which I'm not telling you now.
Okay. Well, yes. So the idea is that we... the torsion, the Galois representation governs the Kummer representation. So we need to start from Galois representations that are probably not surjective modulo 5, that show some of these problems. And if we start from there, then we can somehow, but our approach was more sort of educated brute force, let's say. So we start with these necessary conditions that the Galois representation is not surjective, and then we ran over a bunch of curves with our software, a bunch of curves that show this property, and we see what happens, and we find one at some point. We never had, even in cases like for the prime 163, where we had not so many known curves which show non-surjective modulo 163 representation, we were able, after a couple of curves, to find one. So, yeah.
Okay, thank you very much.
Thank you. Then the examination shall be continued by Professor Lenstra.
Dank u wel, meneer de rector. Meneer de kandidaat, I greatly enjoyed reading your thesis because it is on the subject that is close to my heart, and I was very happy to see someone work so hard on it with methods that were so sensible. My enjoyment, I decided to start on a random page, and that random page was number 112. And I would like to ask you a question about lemma 2.10, since I did not completely understand the exact meaning of the conclusion of that lemma. And I would like to submit to your attention an example which I hope you can use to explain what the notation in the lemma means. So I take my partially ordered set to be the set of positive integers, which is ordered by divisibility. And that is actually not just a partially ordered set, but a directed partially ordered set. I do not know whether you omitted that condition on purpose, but that is not what my question is about. And my topological groups, they are just discrete abelian groups. And if I is in capital I, so I is a positive integer, then my ith sequence, well, the middle term, the AI, is just the additive group of integers. And the subgroup, the AI prime, that is also the integers, but the map is multiplication by I. And then the AI double prime is the co-kernel, which is Z mod IZ. And then I also owe you the transition maps, the rho ij. Well, if I divides j, then the transition map is simply induced by the identity map on the middle term, z goes to z. And I would like to ask you what in this example the meaning is of the further notation that I did not yet define for you because you defined it yourself.
Thank you for your question, geleerde opponents. So you mean the notation, the subspace topology and quotient topology? Which notation is problematic?
Well, I think that you have this condition that you have a projective system. There is a slight typo there, which is not so important. There is a script A that needs a little I, yeah, that is, I think, obvious. But then you have this script A that is a limit of this projective system. What are these groups, A prime, A, and A double prime, and what is this exact sequence in the example that I gave you?
Oh, those are the projective limits of the, so if we isolate the A prime or the A double prime, we take the projective limit of this system of groups.
Okay.
So they are topological groups with a topology induced by the limit. And yeah, and we still fit in this final exact sequence.
And
but
then,
it is not clear that the maps are continuous, I think. This is what
and
I
in the
proved.
example that I gave you, what are A prime and A double prime?
So A would be the profinite integers, so the infinite products of the.
The A
would be the profinite integers, so the.
Well, the AI that I defined to be Z, right?
Or just
the
Z.
middle term
Okay,
of my ith sequence is always Z for every I, and the transition maps are always the identity on Z.
Okay.
So if I take the projective limit of that system, what do you obtain?
So transition maps are the identity on Z, so that would be Z.
Yeah, right.
Yeah.
So your capital A in the middle of your last sequence is a Z.
Yep.
Okay, what about the other two?
Well, on the left, we
on the left,
have,
yeah, you have A prime, yeah.
would it be 0, I think?
Yeah, that is true.
Yeah,
That is 0.
because it's
Very
the,
good. Thank you.
it has to be divided by,
Okay,
Yeah.
good.
and then the last one would be the profinite integers. But that would
Okay.
not fit with the isomorphism.
And then what about this last sequence?
Yeah, exactly. It becomes not exact anymore. Yeah.
It is not exact. So what do you mean by the quotient topology if you don't have a surjective map?
Yeah, I guess there cannot be one.
I see. So apparently you have the same problem that I have.
Yeah.
Okay.
Yes.
So that suggests the question where this lemma is being applied.
Yes, I do apply it in. Let me see. I think proposition 3.13 maybe, or maybe earlier. What is this lemma? 2.10.
3. Is it 14?
No, 14 maybe. Yes, maybe 14. But I don't see a reference to this. You know, I use it somewhere. Yes, so here's C lemma. Okay, so it's a discussion between, so it's a discussion before proposition 3.15 on page 120, which is essentially the proof of proposition 3.15.
Okay, so maybe you have to develop an alternative argument there.
Yes.
Do I have time for an additional question?
A very short one.
Very short one. Okay, a short question. Does Schinzel's lemma, Schinzel's theorem, play any role in your thesis?
I have not used it explicitly, I think, but Schinzel's theorem is about Kummer extensions of a kind, of a classical sense. I'm may have some of my results which are analog of Shinza's theorem for Kummer extensions, for elliptic curves. Yeah.
Okay,
But
thank
I
you very much.
would not be able to point at which exactly right now.
Thank you. The examination shall be continued by Professor van Luik.
Dank u wel, meneer de rector. Meneer de kandidaat, I also enjoyed very much reading your thesis. I would like to ask a question about proposition 7, but given that we've already had people read this, let me summarize it. You start with a number n, and you want to check whether it's divisible by prime p. And you have a nice check. All you do is you take the last digit, you multiply it by some number, e prime p, and you add it to the other, to the remainder, if you leave out that last digit. This smells like it could be an algorithm. So I have a couple of questions about this. First of all, why the prime on the e?
It's a bit of a joke. Oh, sorry, thank you for your question, geleerde opponents. So the origin of this proposition is that it was a night I could not sleep. It was too hot in a hotel room, and I didn't know what to do to entertain myself. So I used this, tried to develop a general result for divisibility criterion. I knew the one for 7, and I knew that 14 had a similar one. And when I wrote it down a few days later, I wrote it online, on Facebook, I think. And I started using, so the statement was not this polished. It was a very confused proof, and I had to use many letters. And at some point, I ran out of letters that were suitable for something, so I decided to use E with a grave accent on it, just randomly, I think.
Okay. My next question is it important that p is prime?
Well, it is important that it is invertible modulo 10.
And I think that's probably the only thing, maybe.
I do not think it is important that it is prime, no.
I completely agree. So I already said you don't phrase it as an algorithm, but it smells like an algorithm, of course. Is this efficient? And also, when do you stop? What do you do at the last step?
I do not think it is efficient. And essentially, the last step, so when you have, well, it depends on the prime, what the last step is exactly. I guess you'll have to do on a case-by-case basis to check whether you need a finite list of prime. There is going to be some bound after which you don't need to know, after which you apply this recursive algorithm. And then for a finite set of small numbers, small multiples of p, you have this finite list, and you just check which your number is in this finite list. I guess this would be an implementation of this algorithm.
Okay, and do you always get that low? I mean, does the number always become smaller? And if you
this number, EP, is at most. So what is x is the...
I can already give you a very silly answer. The answer is no, it doesn't always become smaller.
Okay,
if you start with just one digit, 7,
of course, no.
Your prime is 3. But could it, so then nothing happens, right?
Exactly.
But could it even become bigger?
So you take the last digit, you multiply it. I have not checked myself. I guess
so let's
it is
check.
possible.
So let's check.
Okay.
Let's take p equals 13.
13, yes. So the last digit is 3. So I have to take 3x plus 1, but x is
so e is equal
1.
to?
E is equal to 4.
And now we're going to take n equal to 19.
N equal to 19. So we have, 4 times 9 plus 1 is definitely higher than 19. Yes.
So yeah, you get to 37, right? So you actually become bigger.
Yes.
So is this a problem?
Well, for an algorithm, it would be a problem, yes. But this was not stated as an algorithm.
No,
it was stated as a...
Hora est.
Mr. Candidates, the time allotted to the examination of your dissertation and its propositions has passed. The committee withdraws in order to deliberate, and I request that you and your company await our return here. Mr. Candidate, we have examined your dissertation and the propositions appended thereto. We have heard your defense and we have considered the report by the faculty concerning your previous study. On the basis of this, we have decided to admit you to the doctorate. Professor Stevenhagen is empowered to confer that dignity upon you in the customary fashion.
Volgaarne aanvaard ik de taak mij door de rector magnificus der universiteit opgedragen. Uit kracht dan van de bevoegdheid ons bij wet toegekend volgens het besluit van de commissie hier tegenwoordig verklaar ik bij deze u, Sebastiano Tronto, te bevorderen tot doctor. Ten bewijze hiervan zul je het diploma door rector, secretaris en promotor ondertekend en met het grootzegel der universiteit bevestigd ter hand worden gesteld. Nadat ik alzo de mij opgelegde taak heb volbracht, mag ik de eerste zijn die u als dokter begroet en met de verkregen waardigheid gelukwens. Waardeer haar als een eervolle onderscheiding en een welverdiend voorrecht, maar vergeet daarbij nooit de verplichtingen die zij u oplegt jegens de wetenschap en de samenleving. Vu le fait que la thèse que vous venez de défendre a été complétée en co-tutelle entre l'Université de Leiden et l'Université de Luxembourg, je continue mon texte formel pour un moment en français, qui est une des langues officielles de l'Université du Luxembourg. La langue néerlandaise n'est pas parmi ces langues. Le jury de thèse, représenté ici par son président, monsieur le professeur Wiese, m'a demandé de vous faire savoir qu'elle a décidé de vous décerner le titre de docteur de l'Université du Luxembourg. Je ne connais pas les obligations qui viennent avec ce titre luxembourgeois, mais je vous félicite pour la réussite. Alvorens de rector nu afsluit, hebben we nog een ander belangrijk onderdeel, de laudatio, die zal worden uitgesproken door professor Peruca.
Dear Dr. Tronto, caro Sebastiano, congratulations on having obtained your doctoral degree. It is my pleasure to say a few words also on behalf of your Leiden supervisor, Peter Pre. After your Algen Master in Milano and Leiden, you continued your journey in number theory by starting a PhD in Luxembourg and Leiden. Your PhD project was the first Luxembourg-Leiden co-tutelle in number theory, and more students will follow your steps. At the beginning of your PhD, I proposed a number of projects for you to work on, and you took this on with a lot of energy and insight. From the start, you had a very productive collaboration with your fellow PhD student Pietro Sgobba and myself, resulting in several papers. You also began working with Davide Lombardo from Pisa, which led to the first part of your thesis. Building on this experience and inspired by discussions with Hendrik Lenstra, Peter Stevenhagen, and Peter Bruin in Leiden, you independently developed the general algebraic framework for Kummer theory, which resulted in the last part of your thesis. You made the best possible use of your time at both our universities, also in aspects other than research. In Luxembourg, you received a teaching award last year, and you engaged in outreach activities to popularize mathematics. In the Netherlands, you were one of the 4 finalists for the annual PhD prize of the Dutch Mathematical Society. Besides mathematics, you are a competitive programmer, and you set a new world record for solving a Rubik's Cube in the smallest number of moves. For the next step in your career, all doors were open to you, and you have chosen a job that perfectly combines your mathematical abilities and your computer skills. For us, as supervisors, it has always been a great pleasure to work with you. We wish you all the best for your future. Let's keep in touch.
It is an agreeable duty, very learned sir, to congratulate you upon your degree also on behalf of the university and its Council of Deans. And herewith I declare the ceremony closed.